Okay, so before we move on to the next topic, I want to introduce here an important and major problem which is associated with the concept of multiple processes and multiple resources. So it's something known as a deadlock. So you might have come across the term in the computer science context or outside of it, and it means more or less the same thing. So a deadlock is basically where two or more people are locked in a situation, and we call it a deadlock because nothing really can be done to get out of it, right? So in the context of processes, for example, we are going to take this example where we have P0 and P1. I apologize for the poor quality of the image. So you have two processes, P0 and P1, and we have two resources, S and Q. So we'll take a look. Let's say you have S over here and Q over here, and as of now both these resources are free. No one has made any claim on them. So P0 and P1 arrive in the queue at roughly the same time, and they are both being executed concurrently. We have multiple cores. Multi-core programming is something you're well versed with by now. So one CPU is dealing with P0, the other CPU is dealing with P1. More or less parallelly both of them are running. So P0 is calling the wait function on S. So now if you know the definition of wait, now the wait can be defined as a semaphore or a monitor, makes no difference for this context for our purposes. The wait function is going to check whether this resource is available. If it is available, it's going to acquire it. If it's not available, it's going to wait. As of now, our S resource is available, right? No one has taken it yet. So P0 is going to take S. So this one is taken up by P0. Meanwhile, P1 is taking a wait on Q. Again, Q is also not taken so far by anyone. So P1 takes up Q. So the first instruction done. Next, P0 is waiting for Q. So this resource is needed by P0. So it comes here, it issues a wait function, meaning this one is already taken up. So P0 has to wait. So P0 is waiting. Right. Meanwhile, on this side we have P1 issues a wait call for S. So P1 comes here, sees that this has been taken up. So here P1 is waiting. Alright, so these two have been executed, but P1 has not acquired S yet. P0 has not acquired S yet. So this critical section and this critical section cannot be executed yet, right? So this wait function is completed only when P1 gets to access S, and similarly when P0 gets to access Q. That has not happened. So we are both standing here and waiting, right? P1 is waiting for S, P0 is waiting for Q. Now, how will P1 get access to S? It will happen only if P0 signals the release. Do you get what I'm saying? S is currently taken up by P0. Only if P0 signals the release, P1 can get access. So for this statement to happen, wait of S to happen, this signal of S, right, so if you want this wait of S to happen, right, if you want this wait of S to happen, that is to complete happening, meaning if you want P1 to get access to S, then P0 needs to signal S, meaning this thing needs to happen. For P0 to signal S, it should deal with its critical section and finish it off. For that critical section to be dealt with, P0 needs access to Q, correct? And for that Q to be given to P0, P1 needs to signal its Q. Again, for P1 to signal its Q, it needs to finish its critical section, for which it needs S. So basically it's a cycle kind of a thing. You have P1, P0. So this one needs this one's resource to finish its job. This one needs this one's resource to finish this job. So both of them have one resource each and do not have one resource each, which is with the other person. So ultimately neither of them can finish their job, because of which they don't give up their resource, because of which the other person can also not finish their job. So this kind of a situation is called a deadlock. Now intuitively it will seem to you like a simple thing. Why can't one of them just break midway and give up the resource? the other person will finish everything and then hand back both, then the first one can work on it again. Well, even in case of human beings, that's not always how it works, right? You have two people fighting for a thing, both of them might not be ready to give up. So that's one thing. And with processes also, with processes it's a very mechanical thing, right? They do what they're told to do, they do what their processor tells them to do, and the processor works in a very organized sort of way. Even for scheduling, you saw 5-6 different algorithms. So the processor cannot just arbitrarily choose one process and say you do your work, you give up your resources. So there needs to be some formal mechanism for dealing with this situation. There is, and we are going to look at it in detail in a while. For now, all I want you to know is what a deadlock is, which is basically two processes which both have some resources which the other person wants, and because of which neither is able to finish its critical section and give up the existing resources. So both of them are stuck in a loop, neither is moving forward. So it's like there's a closed door and two people come to open the door at the same time, and both of them end up saying you go first, you go first, you go first. Nobody is going in. So they're both standing there at the door. That kind of a situation is called a deadlock. So we will look at this more formally and see how to avoid, how to prevent, how to recover from this in detail in a while.